All right, let's go.
Number 13, the paradox itself. The grandfather paradox has a precise logical structure, not just a science fiction premise. A person travels backward in time and kills their own grandfather before he has children. If the grandfather never has children, one of those children never grows up to become the time traveler's parent. If that parent is never born, the time traveler is never born either. And if the time traveler is never born, there's no one left to travel back in time and commit the killing in the first place, which means the grandfather survives, has children, and the time traveler is born after all, closes the loop, and goes back to try again. The scenario doesn't just fail to make sense, it actively contradicts itself in both directions simultaneously, which is what separates a genuine paradox from an ordinary plot hole. The concept appears in early 20th century science fiction, with French writer René Barjavel developing one of the first detailed explorations of the self-negating time travel scenario in his novel Le Voyageur Imprudent. But the underlying logical problem is older and more fundamental than any specific story. It's a direct consequence of allowing an effect to erase its own cause, a structure philosophers call a causal loop with no consistent resolution. What makes this more than a thought experiment is that general relativity, Einstein's own theory of gravity, does not mathematically forbid the kind of backward time travel the paradox requires. That's not a flaw physicists discovered by accident, it's a feature of the equations themselves, and it's exactly why the rest of this list exists. Number 12, the loophole in relativity. Special relativity, Einstein's 1905 theory, absolutely forbids traveling into your own past. Space and time are locked together in a way that keeps cause reliably before effect for every observer in flat, uncurved space-time. General relativity, published a decade later, changes the situation because it allows space-time itself to bend and warp in the presence of mass and energy. Once curvature enters the picture, the strict separation between past and future that special relativity guarantees is no longer automatically preserved everywhere. A closed time-like curve, or CTC, is the technical term for a path through spacetime that loops back and intersects its own past. A trajectory where, moving only forward through your own local experience of time the entire way, you eventually arrive back at an event you already left. Physicists have found a genuinely large number of independent solutions to Einstein's field equations that permit CTCs to exist somewhere within them. Rotating universes, spinning infinite cylinders, rotating black holes, cosmic strings, and traversable wormholes all appear on the list, discovered by different researchers working independently across nearly a century. This is the uncomfortable starting point for everything that follows. CTCs aren't a fringe idea smuggled into physics by time travel enthusiasts. They're a mathematically legitimate consequence of general relativity discovered by mainstream physicists solving Einstein's own equations, which means the grandfather paradox isn't just a philosophical puzzle, it's a genuine problem that theory has to answer for. Number 11, the rotating universe. In 1949, the mathematician Kurt Gödel, working alongside Einstein at Princeton's Institute for Advanced Study, found an exact solution to the field equations describing an entire universe filled with rotating matter. Gödel's solution wasn't a technical curiosity buried in an appendix. It directly demonstrated that closed time-like curves exist for every observer within that universe, meaning that, in principle, a traveler with a fast enough spacecraft could journey out, loop around the universe's rotation, and return to any point in their own past. Gödel didn't propose the solution as a serious cosmological model. He proposed it, at least in part, to make a philosophical argument. If general relativity permits a universe where the past can be revisited, then the intuitive, common-sense idea of time as something that flows in one fixed direction can't be a necessary feature of physical law. It has to be a contingent fact about the specific universe we happen to live in, not a logical requirement. Observational evidence has since made clear that our actual universe is not rotating in anything resembling the Gödel's model requires, so nobody treats his solution as a description of physical reality. What it proved instead has outlasted the specific model. General relativity on its own does not rule out the past being revisited. That single result reshaped the entire subsequent debate. Number 10. The spinning cylinder. In 1936, physicist Willem Jacob van Stockum solved the equations for an infinitely long, rigidly rotating cylinder of dust, without initially realizing his own solution contained closed time-like curves. Decades later, in 1974, physicist Frank Tipler picked the idea back up and showed explicitly that if such a cylinder were massive and dense enough and spun fast enough, it would drag the space-time around it so severely that light and matter near the cylinder could, in principle, be redirected into loops running back into their own past, a phenomenon now generally referred to as a Tipler cylinder. The catch, and it's a serious one, is scale. Van Stockum's original solution required a cylinder of genuinely infinite length to work cleanly, which obviously cannot exist in the real universe. Tipler's finite version requires a cylinder spinning at a substantial fraction of the speed of light while remaining under enough gravitational density not to collapse into a black hole first. A combination of mass, density, and rotational speed almost certainly beyond anything that could ever actually be built or occur naturally, even by the standards of exotic astrophysics. Tipler cylinders occupy a specific, useful place in this discussion. They're not dismissed as mathematically invalid the way some other proposals eventually were. They're a legitimate solution to Einstein's equations that happens to demand engineering so extreme it functions as a practical rather than theoretical barrier against ever actually testing whether the paradox it enables would really occur. Number 9. The Ring Singularity. Unlike Gödel's universe or Tipler cylinder, rotating black holes are not exotic hypotheticals. Physicist Roy Kerr solved Einstein's equations for a spinning black hole in 1963, and the Kerr solution is now the standard model astrophysicists use to describe real, observed black holes, nearly all of which rotate to some degree as a consequence of how they form. Inside a Kerr black hole's event horizon, the mathematics describes something genuinely strange. Rather than the crushing single point of infinite density found in a non-rotating black hole, the singularity takes the shape of a ring. Some interpretations of the Kerr solution's interior geometry suggest that mathematically, it's possible to construct closed time-like curves in the region very close to that ring, trajectories where an observer could, in principle, orbit back into their own past. The consensus among physicists is that this shouldn't be read as an invitation. The interior structure of a real, physically formed Kerr black hole is expected to differ substantially from the clean, idealized mathematical solution once realistic factors like infalling matter, radiation, and quantum effects are included. Many researchers expect the ring singularity's exotic causal structure to be unstable or entirely disrupted in any black hole that actually forms from a collapsing star. It remains one of the more genuinely unresolved entries on this list, not clearly forbidden and not remotely accessible either, since surviving passage through an event horizon in the first place isn't something anything is known to do. Number 8. The Wormhole Machine. In 1988, physicists Michael Morris, Kip Thorne, and Ulvi Yurtsever published what remains the most detailed engineering blueprint for turning theoretical space-time shortcuts into an actual time machine. Their starting point was the traversable wormhole, a hypothetical tunnel connecting two distant points in space-time held open by a form of matter with negative energy density, since ordinary matter's gravity would otherwise cause the tunnel to collapse. Their key insight was that a wormhole doesn't automatically create a time machine on its own, but if one mouth of the wormhole is accelerated to a significant fraction of the speed of light and brought back, or lowered into a strong gravitational field and returned, time dilation causes the two mouths to age at different rates relative to each other, exactly as ordinary relativity predicts for any two clocks in relative motion or different gravitational potentials. Once that time difference accumulates, stepping through one mouth of the wormhole and out the other becomes functionally identical to stepping into the past. This proposal is taken seriously specifically because it doesn't require any exotic new physics beyond what relativity already permits elsewhere. Only negative energy density, which has been observed in small laboratory-scale quantities through the Casimir effect, just never remotely close to the scale, density, or stability a real traversable wormhole would demand. Number 7. The self-consistent universe. Given that closed time-like curves keep surviving contact with Einstein's own equations, physicists needed an actual answer to the grandfather paradox rather than just a list of places it could theoretically occur. In the mid-1980s, Russian astrophysicist Igor Novikov proposed what's now called the Novikov self-consistency principle. Any event that would create a genuine paradox in a spacetime containing closed time-like curves simply has a probability of 0. The only physically permitted histories under this framework are ones that are already, globally, self-consistent from beginning to end. Under Novikov's principle, you could genuinely travel back and attempt to kill your grandfather. You just could never actually succeed. Something would always intervene. A stuck door, bad timing, a missed shot, unrelated bad luck. Not because a supernatural force stops you, but because any timeline where you succeeded was never a valid solution to the physics in the first place. Every version of events that's physically permitted to happen is, definitionally, one where you were already destined to fail. This isn't a philosophical patch bolted onto the physics. Novikov and collaborators, including physicist John Friedman, formalized it mathematically in a 1990 paper on the Cauchy problem in spacetimes containing closed time-like curves, treating self-consistency as a genuine boundary condition equations must satisfy. The same category of requirement as conservation of energy, not an ad hoc rule invented specifically to dodge the paradox. Number 6. The billiard ball problem. Novikov's principle sounded reasonable in the abstract, but in 1990, physicist Joseph Polchinski challenged Kip Thorne to prove it actually worked, using a scenario designed to strip away every complication of free will and human decision-making. Imagine a billiard ball launched into one mouth of a time-traveling wormhole on a precise trajectory that would send it out the other end 30 minutes in the past, on a collision course with its earlier self, a hit hard enough to knock the earlier ball completely off course and prevent it from ever entering the wormhole in the first place. A perfect mechanical grandfather paradox with no psychology involved at all. Two of Thorne's students, Fernando Echeverria and Gunnar Klinkhammer, worked through the actual physics and found something unexpected. The ball does still travel through the wormhole. It does still return and collide with its earlier self. But instead of a direct hit that erases the trajectory entirely, the collision is a glancing blow, one that nudges the earlier ball's path by exactly the angle needed to send it into the wormhole at precisely the trajectory required to come back out and deliver that same glancing blow. The 1991 paper documenting the result found not just one such solution, but an entire family of self-consistent outcomes for the same starting conditions. The billiard ball problem matters because it moved Novikov's principle from a philosophical assertion to something demonstrated through actual equations of motion. Nobody had to inject a mysterious force into the scenario to prevent the paradox. The self-consistent solution was simply already sitting inside ordinary Newtonian mechanics once time travel was added to the setup. Number 5. The branching timeline. Not every physicist finds Novikov's fixed, unalterable single timeline satisfying, particularly because it removes any meaningful sense of choice from a time traveler, who, on this model, can never actually change anything they set out to. An alternative, popular resolution, borrows directly from the many worlds interpretation of quantum mechanics developed by physicist Hugh Everett in 1957. Instead of one single, self-consistent history, reality is constantly branching into separate, equally real timelines every time a quantum event could go more than one way. Under this framing, a time traveler who journeys backward doesn't return to their own original past at all. They arrive in a new branch that splits off at the moment of their arrival, a timeline that was identical to their own right up until they showed up in it. If they kill their own grandfather in that branch, they've simply created a new timeline where that specific version of them from that specific branch is never born. Meanwhile, the original branch they departed from continues on completely unaffected with their own history and their own birth fully intact. This approach cleanly eliminates the logical contradiction, since nothing about the traveler's own existence in their home timeline was ever actually threatened. What it doesn't do is offer any confirmed physical mechanism connecting many worlds branching, a genuine feature of quantum theory's ongoing interpretational debate, to closed time-like curves, a genuine feature of general relativity. The two frameworks were developed independently, describe different regimes of physics, and have never been formally unified in a way that makes this resolution more than a conceptually appealing analogy.
Number 4. The quantum fixed point. In 1991, physicist David Deutsch proposed a genuinely different kind of resolution, grounded directly in quantum mechanics rather than general relativity or philosophical argument. Deutsch's insight was mathematical. Any quantum operation, even one that isn't perfectly reversible, is guaranteed to have at least one fixed point, a state that comes out of the operation exactly as it went in. Deutsch proposed that nature simply enforces this fixed point around any closed time-like curve, which became known as the DCTC model. Applied to a quantum version of the grandfather paradox, a particle that travels around a loop and flips the state of the very particle that created it, Deutsch showed the contradiction dissolves if the particle exists in quantum superposition rather than a definite classical state. The particle can be, in a precise sense, part in the state that survives and part in the state that doesn't, simultaneously, in a way that's fully self-consistent once the mathematics is worked through, rather than a definite object that either exists or doesn't. Deutsch's model remains genuinely contested rather than settled. Some physicists have pointed out that it implicitly relies on an expanded multiple world-style picture of reality that goes beyond standard quantum mechanics to make its conclusions work, and it's not universally accepted as the correct account, even among researchers who take closed time-like curves seriously. What it did accomplish, regardless of that dispute, was prove that a full quantum treatment of the paradox produces a mathematically consistent, non-contradictory answer, not just a hand wave, but an actual worked resolution.
Number 3. The post-selected particle. A separate quantum approach developed by physicists Seth Lloyd and collaborators at MIT models closed time-like curves using post-selection, a technique already used elsewhere in quantum information theory, where only the outcomes of an experiment that match a specific desired condition are kept and all others are discarded. Under what's called the PCTC model, a time-traveling particle is treated as being quantum teleported into the past, with the mathematics of teleportation naturally forcing the outcome into a self-consistent form. In 2011, Lloyd's team went further than pure theory and built an actual tabletop demonstration, published in Physical Review Letters. Using photons and standard present-day quantum optics equipment, they simulated a quantum version of the grandfather paradox, a photon effectively interacting with its past self through a teleportation and post-selection circuit, and confirmed the system settled into the self-consistent outcome the PCTC math predicted, without any contradiction appearing anywhere in the results. It's important to be precise about what the experiment did and didn't prove. No photon traveled backward through actual time, and no real closed time-like curve was created in a laboratory in Massachusetts. What the team built was a faithful simulation of the mathematics that would govern a real CTC, run entirely using ordinary forward-flowing time. It's the closest thing to physical evidence anyone has produced that a quantum resolution to the paradox is mathematically stable, genuinely useful, and genuinely not the same thing as time travel itself.
Number 2. The vacuum's defense. Not every physicist accepts that closed time-like curves would ever be allowed to fully form in the first place. In 1992, Stephen Hawking proposed the chronology protection conjecture, the idea that the laws of physics themselves, specifically quantum effects, actively prevent time machines from ever being completed, regardless of which classical general relativity solution someone tries to use to build one. The mechanism Hawking pointed to involves vacuum polarization, the way empty space at the quantum level is never perfectly empty, constantly producing and reabsorbing virtual particles. Multiple independent calculations have found that as any spacetime geometry approaches the exact configuration needed to form a genuine closed time-like curve, the quantum vacuum energy circulating through that region diverges toward infinity, growing without bound right at the critical threshold, a runaway feedback effect that, in most of these models, would destroy the very structure, whether a wormhole throat or a rotating cylinder, that was being used to build the time machine moments before it actually finished closing the loop. Hawking, only partly joking, pointed to a simpler piece of supporting evidence: the absence of visitors from the future, given how many people across history would presumably have wanted to visit. The chronology protection conjecture has never been formally proven. Some researchers have found specific model spacetimes where the divergence doesn't clearly appear, keeping the question technically open, but it remains one of the most widely respected positions in the field. Not that the paradox is unsolvable, but that nature may simply never let the setup exist long enough for the paradox to become a real physical problem in the first place.
Number 1. What actually gets resolved? Line up every entry on this list in a specific pattern holds without exception. Nobody working seriously on this problem has ever found a version of physics where you travel back, kill your own grandfather, and the universe simply breaks. Every framework that takes closed time-like curves seriously, Novikov's fixed self-consistent history, the billiard ball's glancing blow, Deutsch's quantum fixed point, Lloyd's post-selected particle, converges on the same underlying shape, a version of events where the paradox-generating action is either physically prevented, mathematically reinterpreted into something that no longer contradicts itself, or blocked from occurring by the geometry giving out first. Hawking's chronology conjecture goes a step further and questions whether the setup would ever be allowed to finish forming at all. That convergence is the actual finding more than any single theory on this list. The grandfather paradox was never really a proof that time travel to the past is logically impossible. It was a genuine constraint, a description of the one specific outcome that consistently fails to appear as a valid solution across every serious mathematical framework anyone has applied to the problem, whether built from general relativity, quantum mechanics, or an experiment using nothing but photons and mirrors on a bench in a lab. None of this has been tested with an actual closed time-like curve, and given the scale of Tipler cylinders, the stability problems inside Kerr black holes, and the exotic matter requirements of traversable wormholes, none of it may ever be. What's been tested repeatedly across nearly 40 years is whether the paradox itself survives contact with real physics. So far, in every framework anyone has managed to fully work out, it hasn't.
13 ways physics has approached the same closed loop, from Gödel's rotating universe in 1949 to a photon on a laboratory bench in 2011. None of them found a version of events where killing your own grandfather actually works. Only versions where something, whether a law of probability, a quantum fixed point, or a collapsing wormhole throat, quietly steps in first. The paradox that seemed on its surface to prove time travel was logically impossible turned out to be something much narrower and considerably more interesting: a precise description of the one outcome the universe, across every model built to test it, has never once allowed to happen. Subscribe to Cosmic Hives. See you in the next one.